Lesson 8 looks at comparing two independent means, and we're going to do so today using both a confidence interval and a hypothesis test. So as a reminder, our formula for both is based off of the same model. It's based off the central limit theorem. That says that x bar follows a t-distribution with a degree of freedom of n-1, and a center or an average of mu, and a standard deviation of s over the square root of n. Taking this formula and writing it as an interval, I get x bar plus or minus t star, s over the square root of n. Confidence intervals are based off of samples. So I'm just taking that mu, I'm writing it as an x bar, sample, s, already sample, I'm leaving it as s. In contrast, hypothesis tests are based off of claims. And this is going to work a lot like the lesson where we compared two proportions. So I'm going to look at some of the commonalities here. First off, I just want to make sure that I understand how to look at the difference of two groups. So suppose for the project for this term, I'm comparing the average cost of groceries at Safeway and grocery outlet. If I do Safeway minus grocery outlet and get a positive number, well, this tells me Safeway minus grocery outlet is bigger than 0. Moving grocery outlet to the other side by adding it, this tells me that Safeway costs more than grocery outlet. So if I'm in a situation where I have a large number minus a small number, that's how I end up with a positive. If I have a sign that is greater than 0, that tells me the first group is bigger. Let's suppose I do Safeway minus Fred Meyer, two different stores here, and I get that this is less than 0. Well, moving Fred Meyer to the other side, I'm just adding it over. This tells me that Safeway, on average, costs less than Fred Meyer. Now, finally, let's suppose that I end up with something like Safeway minus Albertsons equaling 0. When I was looking at those confidence intervals for two proportion, a reminder, if I had a negative and a positive in my interval, that told me the results were inconclusive. It told me that the two things could be equal to each other. And I can see that here just by taking this average for Albertsons and adding that to the other side. So if 0 is inside of my interval, then that tells me the two groups could be the same. So this is exactly the same first page as what was going on for two proportions as far as comparing things to 0. And the reminder is, if I want to compare two groups, and this time I'm going to compare two group averages, then I want to look at the difference in the two averages. So previously I had a model that looked at a single x bar. My goal for this lesson is to find a model that looks at the difference of two x bars, an x bar 1 and an x bar 2. So to make this next page a little bit shorter, reminder for what was going on for proportions. For proportions, I essentially had my p-hat model for the first group, and then to compare this to a second group, what I did was I ended up subtracting the centers, and then for the spreads, I had the spread of the first group, I had the spread of the second group, and I ended up adding the spreads. The reason for this, if you'll recall, this negative here, that's from looking at the difference. This positive is really a negative times a negative. So when I'm looking at variance, things end up getting squared. So that's why I have a positive here. This is really some sort of a negative times a negative that's giving me this plus sign. So what I'm going to do for my model now, and I have this nice page that kind of develops where this is coming from. I would recommend trying to go through and seeing if you could rederive this, but I'm just going to go for it. X bar has a t distribution with some degrees of freedom. We'll talk about that in a second. Average of mu and a standard deviation of square root of s squared over n. I'm going to pause there for a second because I know this looks a little bit different than the model that we just had on the last page. But x bar follows a t distribution, center mu, and I used to have s over the square root of n. A quick double check. The square root of s squared is s. This is s over the square root of n. It's the same thing that my model was before. Why might I want to write it like this? Well, I'm going to have one mondo square root, and I want the square root to cover everything. So I want this to be a big square root with that s squared there. I know I can simplify it, but I don't want to. So I have all of this information for the first group. And I'm going to compare this to that same information for the second group. When I'm looking at the centers, I subtract the centers. When I'm looking at the spread, I add the spread. So my model for x bar 1 minus x bar 2 follows a t distribution. Center of mu 1 minus mu 2, I'm going to label this thing as my center. And standard deviation of square root of s squared over n plus s squared over n for my respective groups. Now, I personally feel like if I'm working with two groups, then for strength, I always feel like I am as strong as my weakest member. So for degree of freedom, I like to take the smaller of the two degrees of freedom. Here's what I mean by this. If I do a research project with someone and I have 100 samples, but they only do 5 samples for their group, I'm not 100 strong. I'm as strong as my weakest group. I'm really 5 strong. And the degree of freedom for 5 would be 4. So I personally, this is a really pessimistic way of kind of looking at it. I take the smaller of the 2 degrees of freedom when I'm trying to figure out my DF. Now, the actual formula for the degree of freedom is a little bit messier than that. It involves all the standard deviations. It involves this n1 minus 1 business where I'm weighting and squaring things. And even when I do this, it doesn't always give me a whole number. So sometimes it'll say I have a degree of freedom of 8.5. I still would have to make a judgment call. Do I treat that like 8 as my degree of freedom, or do I treat that as 9 as my degree of freedom? So if you use your calculator to kind of double check things, you may notice that your degrees of freedom are really different than what we're going to be doing in class. However, if you're using this lie, and I'm going to underline this because I am lying to you a little bit, but I'm telling you how I am lying to you. My DF might be different, but my confidence intervals and my hypothesis test are going to be really, really close. So for example, instead of a p-value of 0.002, I might have a p-value of 0.0021. It's going to be so close I can't tell the difference in almost every situation. So as we're going through, if you want to use this longer formula, you're welcome to do that. But I'm going to continue to use this quick estimate to just try to figure out what's going on. So for example, if I have a group of 100 and a group of 31, and you asked me what the degree of freedom was, I would base it off of that weaker group. And I would say the degree of freedom is 1 less than 31. I'm rocking a degree of freedom of 30. Next problem, a group of 11 and a group of 200. My weaker group there is 11. My degree of freedom would be 1 less than that. I'm looking at 10. I now have my model for this distribution, and believe it or not, this means I'm almost done with the entire lesson. I now can use this one model to come up with both my confidence intervals and my hypothesis test. We're going to start with confidence intervals. So reminder for confidence intervals, their center plus or minus whatever distribution you're using, and this time we're using t-scores, multiplied by your standard error. So what I'm going to do is I'm going to take my center, I'm going to take my standard deviation, and I'm going to put these things inside of my formula. As I put them inside of the formula, I just have to remember that I'm writing everything as samples because confidence intervals go from samples to population. So I used to have a center of mu1 minus mu2. The sample way of saying this is x bar 1 minus x bar 2. Plus or minus. I'm working with t-scores, so I have t stars that I'm going to be looking up. And I have my t-table on the ready today, so we're going to be looking at that a lot. And my standard error is s squared over n for the first group. If I just stopped here and I only looked at the one stuff, I have x bar plus or minus t star, s over the square root of n. I have my old formula for the confidence interval that kind of lives inside of this. And I'm going to be adding the same thing now for the second group. There are a couple of assumptions for using this model, the same assumptions that I see for pretty much every model that we work with. I need to make sure that I have a random sample. By that I mean there's no bias in the way the data has been selected. I need to have independence within my first and second group. The backup for this is sampling less than 10% of the population. I call that the 10% rule. And I need to have a large sample. And as we saw in the last two lessons, large N for averages means 30 or more, or it starts as a normal distribution. Finally, not only do I need independence within, as the name of this lesson suggests, I need to have independence between my two groups. I'm comparing two independent averages today. So let's look at an example of this thing from start to finish just to see how everything lines up. It says create a 90% confidence interval for mu1 minus mu2. If the first sample average is 3, standard deviation 2, 25 samples. Second average is 8 hours, standard deviation 1, and sample size of 50. So I'm just going to come up with the template first. And I find that it really helps to just take the model that I had for one average and do it twice. So my old confidence interval formula looked something like this. Because if I simplified this, the square root of s squared, this is really s over the square root of n. So I have x bar plus or minus t star, s over the square root of n. And I have all of this for the first group. I'm going to do it twice. So I'm going to have this for the first. I subtract my center. I add my spread. And I have that same information for the second group. I'm going to plug in everything I know, and I'm going to see that I know almost the entire problem already. X bar for the first group is 3. X bar for the second group is 8. This is going to be a confidence interval for I'm taking the average for the first group minus the average of the second group. So I'm doing mu1 minus mu2. I can see that in my order here that I'm going to be creating it in 1 minus 2 order. This gives me a center of -5 plus or minus t star. Degrees of freedom, well, I have 25 for the first group and 50 for the second. I'm as strong as my weakest link. So I would say my degree of freedom based off the 25 would give me 24. I'm going to have to pull up that table to get that t star. That's okay. My first standard deviation is 2. I have 25 groups. My second standard deviation is 1. I have 50 samples in that group. I have everything but the T star. So I'm going to go to my table, 90% confidence, and degree of freedom of 24. Well, 24 is one of my rows, so I kind of look out there. 24 meets the 90 right there at 1.711. 2 squared is 4, so I'm going to do a little bit of the math as I'm writing this down. 1 squared is 1, whatever this thing ends up giving me. And let me type this into a calculator and see what I get. So I would still call this my best point estimate, or the center. I would still call all the stuff that I'm adding and subtracting the mo. And I believe this is -5 plus or minus, let me type this in. I'm getting that this piece here is 0.73 or so. Doing this once with the minus is going to give me a low value of -5.73. Looking at the problem, I'm noticing that my units for this thing are hours. So this is -5.73 hours. Doing this with the plus, -5 plus that 0.73, this gives me a high value of -4.27 units. There are also hours. I'm noticing that my entire interval is negative. This is negative and this is negative. Negative numbers are less than 0. So my entire confidence interval here is less than 0. And what is this a confidence interval for? Well, this is my confidence interval for mu1 minus mu2. So mu1 minus mu2, my interval for that was smaller or less than 0. I'm back to that first page of my notes when I'm comparing groups. I'm in this situation here where I have Safeway minus Fred Meyer is less than 0. So I'm going to take the symbol that I'm subtracting and I'm going to move that to the other side of the equal sign. I'm going to take the symbol that I'm subtracting, this mu2 here, and I'm going to add that to the other side to get that mu1 is less than mu2. How confident am I? How much? Well, I would say something like I am 90% confident that mu1 is less than mu2 anywhere from, and the numbers here, this is telling me how much more and how much less. So anywhere from 4.27 hours all the way up to 5.73 hours. You'll notice I didn't write these with a negative. I'm not saying -4.27 hours because that negative word is really built into less. So is less is negative, 4.27 as my high, -5.7 as my low. That's giving me my interval there. We're going to try another 1 or 2 of these things just to make sure I can make sense out of the conclusions. And then we're going to do a hypothesis test going through the 4 steps that we always go through when we're dealing with a hypothesis test. So suppose I'm comparing the jumping distance in feet for Victor and Fiona, and I get a -0.04 feet to -0.03 feet. Now, this doesn't mean that Victor jumped into the ground 0.04 feet. This doesn't mean that Fiona jumped into the ground 0.03 feet. This is telling me something about the difference of those 2 individuals. It's telling me roughly who is the better jumper and how much better. If you're watching this video at home, try pausing the video and see if you can come up with the answer for exactly what this is telling me. Who appears to be a better jumper and how much better? If you're feeling good about that problem, also try doing example 12 here. Same idea, but this one has a negative 0.04 feet all the way up to 0.10 feet. Again, pause the video, try it out, then we'll go through it together. This is what I get. These are negative numbers. Negative numbers are less than 0. Moving this to the other side, this tells me that Victor is worse at jumping compared to Fiona, or I am 95% confident Fiona jumps more, anywhere from 0.03 feet all the way up to 0.04 feet. You notice I don't do any math with these numbers. These are already telling me the differences. This one's a little bit trickier because this is a negative number. And we saw in this last case that this negative number tells me that Victor is worse at jumping than Fiona. The positive number, though, this tells me the complete opposite. This tells me that Victor could be a better jumper than Fiona. And now I'm all over the place because I have situations where Victor is worse. I have situations where Victor is better. Reminder, whenever you have a confidence interval that looks like negative and then a plus, this tells me that the results are inconclusive. The reason for this is 0 is in the confidence interval. And if 0 is in the confidence interval, then it could be the case. I'm not guaranteeing this. So all right, could be, and I'll underline it. Could be that Victor minus Fiona equals 0. And if that's the case, then it's possible that there's no difference between the groups. So I cannot really tell who is the better jumper when I end up with different signs. If I have negative, negative, that tells me someone's better. If I have positive, positive, that tells me the other group is better. So matching signs is typically a good thing. Crisscross signs, not a good thing. Now let's say someone did the problem in the reverse order. So we did our interval for Victor minus Fiona, and we got negative 0.04 to negative 0.3 feet. If I wanted to create a 95% confidence interval for the same thing, but flip it and do Fiona minus Victor, let's think about what happens. I used to have 5 minus 2, that would give me something like 3. Flipping it, 2 minus 5, that gives me negative 3. When I switch the order of subtraction, I get exactly the same number, but with a different sign. So I used to have a negative. When I switch the order, that's going to become a positive. I used to have a negative. When I switch the order, that's going to become a positive. Now, for those of you worried that this is going to screw up my conclusion, remember the conclusion for this previous interval was that Fiona was the better jumper than Victor. Let's see what's going on. This is positive, and this is positive. If it's positive, no longer doing Victor first, we're doing Fiona first. If it's positive, then this new interval is greater than 0. Moving this symbol to the other side, this gives me that Fiona is a better jumper than Victor. That's the same thing as saying that Victor is a worse jumper than Fiona. So I can set up the confidence interval however I would like, but I just have to be really, really careful when it comes time for that conclusion and checking the sign greater than 0, less than 0, or inconclusive. Let's do one more example of this confidence interval thing, and then let's take a look at a hypothesis test or two from start to finish. So during a clinical study, it is found that Tylenol lasts 4 hours for headache relief, on average with a standard deviation of 0.5 hours and 150 trials. I'm going to write down some scratch here. So my average for Tylenol, and this is for a sample, so I'm writing sample average in X bar, is 4 hours. The standard deviation is 0.5 hours, and they did this for 150 samples. Advil. The average for Advil is 6 hours, so a lot longer for an average. That sounds good. But the standard deviation for Advil is 3 hours. So Advil might last longer, but it's way less consistent. So I don't know definitively if I actually have evidence of a statistically significant result here, or if things just vary so wildly that I can never really make a firm suggestion as to which medicine to use. This is for 100 trials. Compare using a 90% CI. Okay, check the assumptions that assuming the patients were selected random from hospitals throughout the nation. Okay. I will check the assumptions, but let's get this T star just so I can clear my page a little bit. When I'm trying to figure out the degree of freedom, I'm always going to base it off the weaker group. 100 samples is smaller than 150. So my DF is going to be based off of that 100 number. 100 minus 1 gives me a degree of freedom of 99. I don't know if 99 is going to show up in my table, so I might just end up using 100 anyways. But let's take a look here. Yeah, 99 is not in, but 100 is. Meets the 90. Oh, it's starting to get closer and closer to that 1.645 number. Not quite there. It's still a little bit bigger. 1.660. Okay, assumptions. It says it's random. Great. Independence, and I have the two different types to check. One person taking Tylenol doesn't affect a person taking Tylenol. Advil does not affect Advil. And no cross-contamination. If someone in one room takes Tylenol, that doesn't affect someone in a totally different room taking Advil. So I have random, and my groups do not affect each other. I have both independence within. Tylenol does not affect Tylenol. Advil does not affect Advil. And independence between. Advil does not affect Tylenol. And finally, I need large N. But that's looking pretty good too, because both of my N's, N1 is bigger than 30, and N2 is bigger than 30 as well. So I can go straight to doing my calculation, starting with essentially just making this interval, and I have the choice of doing either Advil first or Tylenol first. I'm going to do Advil first this time. The reason why I might want to do Advil first here is then I'm going to have a large number minus a small number. Gives me a higher chance of making this thing a positive. So I'm going to have my Advil stuff. I subtract my center. I add my spread. I'm going to plug in my numbers. I have 6 minus 4 plus or minus my t star was 1.660. And the nice part about this is I can really do them in either order. So if I accidentally write down the wrong standard deviation first, if I started with that 0.5, I would still end up with the same number. It's very forgiving. I'm going to type this into my calculator once with the plus and once with the minus. And I don't have to go overboard with parentheses. In fact, order of operations does a lot of the work for me. So for example, that's a little hard to see, but 6 minus 4 minus 1.660 square root 3 squared over 100 plus 0.5 squared over 150. I'm almost writing in no parentheses at all, and it's still doing it for me just fine. Units, hours. I'm going to do the same thing, but I'm going to change that minus before my critical value to a plus. When I do that, hard to read, so I'll write it down, 2.503 units here, also hours. +1, +2, my interval for Advil minus Tylenol is greater than 0. Adding Tylenol to the other side. This tells me I have evidence that Advil outlasts Tylenol. Even better than saying that, though, I can say how confident I am and what values I am confident about. In this case, I am 90% confident Advil outlasts Tylenol on average. That's a really important phrase to have here, on average. Anywhere from 1.497 to 2.503 units average. So if I wanted to say something in a commercial like studies show Advil outlasts Tylenol, I would now have enough evidence to do something like that. Now, in a lot of ways, that last sentence, I have evidence that it outlasts. That's a really important sentence on its own, even not knowing exactly how much more effective. So let's just look at the way to do this same data analysis, but using a hypothesis test frame instead of a confidence interval frame. So before I go on to this next page, reminder, there are 4 steps to a hypothesis test. I have my first step, I have to state my hypotheses. Second step, model and assumptions. I've already checked my assumptions, so I'm going to skip that on the next one. Third step, p-value. Fourth step, conclusion. And I'm going to do this for the same data set. So step 1, hypotheses. Step 2, I'm still comparing averages, and I'm still doing this for the Advil compared to the Tylenol group, so I'll come up with the model. Step 3, this is where I calculate my p-value. And down at the bottom, step 4, this is where I will do my conclusion. Let's fill in the gaps and see what's going on. And I'm going to come back to the conclusion. Recall that during a clinical study, it's found that Tylenol lasts 4 hours for headache relief on average, with the standard deviation of a half an hour in 150 clinical trials. In contrast, Advil lasts 6 hours for relief on average, with a standard deviation of 3 hours in 100 trials. This time, however, let's use a hypothesis test to determine if Advil lasts longer than Tylenol. So null hypothesis is always going to have equals 0. When we compare two proportions, we used to have P1 minus P2 equaling 0. The reason for this is a 0 inside of an interval tells you that there is no difference between the groups. And the null hypothesis always represents there being no change or no difference. Alternative hypothesis. I think Advil is a larger number than Tylenol. So I think I'm doing large minus small. A large number minus a small number, like 10 minus 2, will give me a positive number. So when the time comes, this is going to be a right-tailed test. I don't have to write down these notes every single time. I'm just doing this to kind of help me out because this is my first hypothesis test using this new model. X bar A minus X bar T. I'm leaving this alone. This is the name of my model. It tells me I'm going to be subtracting these two averages. My degree of freedom, I'm using the smaller of the two groups. And my center is going to be the average of Advil minus the average of Tylenol, whatever is being claimed in the null hypothesis. My standard deviation will be S squared over N for the first group and S squared over N for the second group. Now I kind of luck out because in the null hypothesis, it's claimed that mu A minus mu T is equal to 0. The claim is that there is no difference between the two averages. And we assume that's true when we're coming up with the model. We're going to look at the likelihood of the sample data are more extreme if this null hypothesis is true. Standard deviation, I have 3 squared over 100 for one of my groups, 0.5 squared over 150 for my other group. I'm going to type this into my calculator and see what I end up getting for that standard deviation. TF is 99 still. And I believe I get 0.303 units hours. Third step is p-value. I'm going to go through the definition of the p-value, and it's going to tell me how to set up the problem. The p-value is the likelihood. I'm going to be looking at the probability of something here, of my sample data. So I'm going to be subtracting the average for Advil minus the average for Tylenol, or more extreme. Or more extreme from the alternative hypothesis is telling me I'm going to be looking for more. My average for Advil was 6. This is the first time I'm using the X bars in this problem. The average for Tylenol was 4. So my value that I'm going to use when I'm doing value minus center over standard deviation, that number is going to be 2. So I'm going to draw out my curve and see what's going on here. It's claimed that there's no difference. 0 is my center. And I'm counting by the standard deviation 0.303. If I'm counting by this, it's going to take me a long while before I hit a number like 2. This is going to be way out there in the boons. I'm looking for or more, so that means I'm going to shade this thing to the right here. This is going to be a really, really small p-value. All the same, I'm going to try to figure out what the low t-score is for this shaded in region and what the high t-score is for this shaded in region. I'll start with the low. Reminder to find my test statistic. That's another name for this t or this z. This is called a test statistic. I take my value minus the center, and I divide that by the standard deviation. This will tell me the number of tick marks I am away from the center. Just kind of eyeballing it, it looks like I'm going to be like 6, almost 7 tick marks away. My value was 2. My center is 0. My standard deviation is 0.303. Typing this into a calculator, I get a t-score of 6.60. This is highly unusual to get a t-score this big. So this corresponded to a difference of 2. The t-score for that was 6.60. Now, I was shading to the right, and I kept shading forever in this direction. So the highest t-score of my shaded in region was infinity. And a reminder to look up t-scores. I'm using my graphing calculator, and I'm using the tcdf function. tcdf works by taking the low value of the interval, the high value of the interval, and then your degree of freedom. In our case, I have tcdf 6.60, comma infinity. My degree of freedom is 99. I'm actually going to put an asterisk there. Reminder, when I'm saying degree of freedom equals 99, I'm lying to you a little bit there. It might be a different number. So in my calculator, I'm going second vars on my TI-84 here. And I'm choosing the option for TCDF. I have my low value is 6.60. My upper value is infinity, so I'm just going to kind of hit 9s a whole bunch of times. My degree of freedom is 99. I'm only going to hit 9 twice there. I'm being a bit more careful with that degree of freedom. And when I hit enter, I get 1 e minus 9. Reminder, this is scientific notation, so this is really the same thing as 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then a 1. For numbers this small, we have the notation of 0 plus, so I don't have to write that many zeros out in the future. In this last problem, we had a confidence interval of 90%. In this problem, I'm doing a one-tailed test. So if I want to be consistent, I'm going to do a quick little doodle to figure out what the relationship is here. If I make a 90% confidence interval in the center, and I'm wondering how big I'm willing to let this right tail be, what my alpha should be, 90% leaves 10 in total for both, or it leaves me 5% in one tail. So if I want to be 90% confident, that's the same thing as using an alpha level of 5% if I'm doing a one-tailed test. Just as a note, if this was a two-tailed test, it would be the size of both of those tails together. A two-tailed test would have an alpha of 10%. Not that it matters at all here, because look how small this is. My p-value is way smaller than pretty much any alpha level that you could reasonably choose. Ours happens to be the neutral value of 5%. If our p-value is low, the null must go, so I am going to reject the null hypothesis. If I reject the null hypothesis, I have evidence of the alternative. In this case, the alternative, going back up to the top, the alternative is Advil lasting longer than Tylenol. So I have evidence that Advil outlasts Tylenol And the magic phrase here to add on average. It's not going to happen every single time, but in the long run, on average, Advil has more of a duration than Tylenol does when it comes to headache relief. If I wanted to know how much more, the thing I'd want to do here is follow this thing up with a confidence interval, but we already did that on the other page. Let's do one more example of this process here. I gave you some calculator instructions at the top of the page. You're welcome to kind of go through these to double check your work. I always expect to see your work done by hand, so this is just a way to see if your answers are reasonable. The process will ultimately be something that you remember longer than just the 2 or 3 step calculator stuff. I'm teaching you to be critical thinkers instead of just button mashers. Example 16, let's do it. Sonia is preparing her spring garden. Last year, she bought sunflower starters from Al's garden store and orchard supply store. She believes that sunflowers from Al's are taller on average. After collecting some data, she found that for 50 sunflowers planted at Al's, plants grew to be on average 6.3 feet with a standard deviation of 1.2 feet. Okay, I'm going to use the subscript of A for Al's. Average for Al's was 6.3. Feet. The standard deviation is the 1.2 feet. As I'm reading, I might want to highlight stuff so I don't make mistakes like that. So I'm seeing an average of 6.3 and a standard deviation of 1.2. The number of samples for this group was 50. For orchards, I'm going to use O for orchards. They sampled 25. I'm actually worried about the 25. I probably have too small of a sample size to do this. Oh, but they tell me it's unimodal and symmetric. In other words, it starts normal, so I don't feel bad about that anymore. The average for this group was 4.8 feet. The standard deviation for that group was 2 feet. Test for a difference and follow it up with a confidence interval. Okay, we'll do. 50 and 25 samples. 25 samples don't have units, just 25 samples. Of these two groups, the weaker one is the 25. It's smaller. So based off of the lie, we will have a degree of freedom of about 24. I'm going to test for a difference, and let's see what this looks like. Difference. Sonia believes that sunflowers from Al's are taller on average. So not just any difference, but actually taller. This sounds directional. So for a null hypothesis, we'll have that there is no difference from Al's compared to orchard. Alternative hypothesis, I think the Al's number is bigger. So I'm going to have a large number minus a small number, something like 6 minus 5. This is going to give me something that should be greater than 0. So it looks like we have another right-tailed test on my side. And I can always choose to have the larger number come first, so I can almost consistently get these right-tailed tests. It's not a fluke that I got 2 of them in a row like this. I made a choice to have this happen. Second step, model and assumptions. I'm just going to do the model part with you. I would encourage you to check the assumptions. I'm going to do A minus T. It follows a T distribution. Degrees of freedom here, 24, as strong as our weakest group. Center is always 0 when I'm comparing 2 groups because it represents there being no difference in the groups. And the standard deviation is the square root of, and I can do this in either order because addition is pretty forgiving, but first standard deviation squared over its n, second standard deviation squared over its n. T distribution, 24 is my degree of freedom. I'm typing that square root into my calculator and I'm going to see what I get. I have a standard deviation of 0.435 or so units for the problem are feet. Third step, p-value. The p-value is the likelihood. I'm going to be looking at the probability of something, of the sample data. So I'm going to take the name of the model. The name was average A minus average T. Or more extreme. Well, or more extreme in this case means more. And I'm going to use the actual numbers. For A, 6.3 minus, for T, 4.8. And T should really be O for orchard. I have Tylenol on the brain. So I'm going to be looking at owls minus orchard. And the value I'm going to be using for the problem is the difference of the two averages. It's 1.5 feet. So I'm going to draw my picture. The center is 0. I'm counting by about 0.435 or so. And my actual difference is way up here. This is going to be another really small p-value of 1.5 or more. So what I want to eventually be able to do is TCDF my low value, whatever my t-score for 1.5 is going to be, comma, this keeps going on for forever, so comma infinity, comma, my degree of freedom is about 24. That's a lie, it's not the real degree of freedom, but it'll end up being really close for my final result. I have to find this t-score. I do that by taking my value, 1.5, minus my center, 0, and I divide this by that standard deviation of 0.435. This gives me something like 3.45 or so. When I do this TCDF of 3.45, comma, infinity, comma, 24, I get something like 0.001 or so. So as a final step, my p-value, let's use a neutral alpha level of 5%. It is smaller than 5%. If the p-value is low, the null must go, so I'm rejecting a null hypothesis. I have evidence. Sunflowers at owls are taller than orchards on average. And if you're thinking, well, fine, they're taller at owls, but significantly taller? Are we talking about like 20 feet taller? Or are we talking about 1 foot taller? How do I know how much taller? And whenever I'm asked a question about how much, I'm really being asked a confidence interval question. So I'm going to take average for owls minus average for orchards plus or minus t star, degree of freedom, square root, first standard deviation squared plus second standard deviation squared over their respective sample sizes. Now I've actually done a fair amount of this problem already. I subtracted the average of 6.3 and 4.8 there was a difference in the average of 1.5 or so. I don't know T star, I'll have to come back for that. But I also know the square root because this was this 1.2 squared over 50 plus 2 squared over 25 number. This value was 0.435. So really the only thing I need is T star for 90% meets that row of 24 for my degree of freedom. And that value sitting in my table is a critical value of 1.711. I'm going to type this in my calculator once with the plus and once with the minus. And I don't have to go crazy with the parentheses here. I have 1.5 minus 1.711 times, and that standard deviation was 0.435. Calculator is hard to read there, I know, but I'm going to be writing down the number. Low value 0.756 feet taller. I'm doing the same thing, but instead of with a minus, I'm going to do it with a plus. 2.244 feet. So earlier when I said I had evidence that sunflowers at owls were taller on average, if I wanted to know by how much, by this much. So I am 90% confident that they're anywhere from 0.756 feet taller all the way up to 2.244 feet taller. Now, for those of you wondering exactly how close the results are when I use my calculator to come up with these intervals, I just want to show you real quick. I'm typing in my information in my calculator. Instructions are above for those of you that want to learn how to do that. Take a moment and read through. When I used my calculator to come up with the values, I ended up getting 0.7 to 2.24 or so. 0.76 if I round, that looks pretty close, a little bit of round off error difference, up to 2.24 or so. That's really close too. So even though my actual degree of freedom ended up being something totally different, this 33 number, using this lie of 24 still ends up being really close. So if I did stat, test, and I did this 2-sample t interval where I typed in all of the values from my problem, I should still end up with a really, really close result, even if it's not perfectly the same. So when I am saying I'm estimating these values using that lie from earlier, they're going to be remarkably close. T-score of 3.45 if I was doing the test, I got 3.45. P-value, if I round this p-value, that's a 0 plus if I've ever seen one, 0.001 or so, 0.001 or so, great. I'm ending up getting the same p-value there. I have the same conclusion. My calculator and my by hand method match up almost perfectly. The only difference is while we're saying 24, if you do this thing in your calculator, the actual degree of freedom is much closer to 33. Okay, we have looked at doing confidence intervals and hypothesis test for one average at a time. And with this lesson, we looked at doing confidence intervals and hypothesis tests when comparing two averages. That's assuming those averages are independent, that the two groups did not affect one another. What I would like to do in the next lesson is lose that assumption and instead assume that those two things are paired together. So for example, if I wanted to compare the cost of groceries, at Safeway and Fred Meyer, it might be useful to look at exactly the same items, say bananas to bananas, milk to milk, just to see how much those two same items vary. This is going to be a process called matched pair, and lesson 9 is all about that. Okay, good to do some math with you here.